Wonderful. First of all, good morning, everybody, and I would really like to thank all the organizer and the KITP for putting together this extremely interesting program. It's too bad I could not make it to Santa Barbara this time, but I hope you'll find our work interesting. So today, indeed, I want to discuss a little bit about application of thermal convection to geophysical problems, and in particular, the interaction between lake and ice morphology with fluid dynamics underneath. So this is a work in collaboration with Zixi Wang and Chao Sun from Tsinghua University and Enrico Calzavarini in Lille in France. If you want to know more details, you can have a look, of course, to our publication, which is indicated here. So thermal convection, as you know, is ubiquitous. You have it, you find it inside stars. We have it in the atmosphere, oceans. And this is also very important when we cook and prepare our food. Now, a very important mathematical model for natural convection is the famous Rayleigh-Benard system. That's a sort of idealization where you have a closed container, and this closed container typically is taken as a cylinder, and you have two walls here: a warmer bottom wall and cooler top wall, and typically adiabatic condition on the boundary. And according to this parameter, to the flow parameter, to the fluid parameters, the height of the cell, you can have different regimes. So you can have a fluid at rest, and so you have conduction, or you can have convection when the fluid moves, and even very turbulent flows inside of the system. So this is a sketch from Leo Carden of some years back. So the control parameter is a Rayleigh number, which is indicated here, and it concerns buoyancy and the cube of the height of the system, temperature difference, and another control parameter is Prandtl number, which is a kinematic viscosity divided by thermal diffusivity. Now, an important parameter, but it is an output of this physical system, is the heat flux. So how much heat goes through the system. If you are in a conductive situation, that it is easy to estimate is just Q delta, which is a temperature difference divided by H. And this Nusselt number is the dimensionless heat flux. So the actual heat flux that you have, for example, due to conduction or convection, divided by the purely conductive case. Now, some recent review on the topic. As I said, this is a very interesting, extremely studied system, but we may wonder if this exists at all in geophysical application. Indeed, it's very difficult to think that you have such closed system in geophysical application, for example, in the atmosphere here. Most probably you may have other physical phenomena that are ongoing, like, for example, the presence of some lateral wind and so on. So the point I want to make is that natural convection is, of course, extremely important in geophysical application, but often you need to get rid of some of the simplification assumptions that have been made in the past. Just to give a little bit of a flavor, for example, of the relevance of mean wind, you can see here a visualization from some numerical simulation that we performed some years back. And this situation is indeed the classical Rayleigh-Benard system, where you have periodic boundary condition, and this is natural convection. So you have a warm plume going up, cold plume going down, and of course you will have here some heat flux, which is way larger than the conductive one. That will correspond to a situation without wind. A little bit below, you can see a situation where now we apply a force, a volume force, so basically a pressure gradient in this system, but it is laterally periodic. And you see already visually that the thermal plume gets deformed because of this wind. Actually, it's quite easy to imagine that this wind can make the thermal boundary layer more uniform, and so it can suppress the instability, which is mainly driven by the dynamics of the plumes. And indeed, this is exactly what is observed here. You can see in this diagram, which is quite complex, you can see that for different Rayleigh number, you may have a behavior with a Nusselt number, which has some value. And as you increase the lateral wind, that will mean increasing this Reynolds tau here, you see that the heat flux, the vertical heat flux, drops and then eventually increase again. So the drop that you observe is indeed due to this stabilization of the boundary layer due to the shear induced by the wind. And then eventually, if the wind is strong enough, mechanical turbulence will kick in and will further increase the heat flux. So that was just a little bit an appetizer to show how additional physical phenomena can interplay with the natural convection, making it more interesting. But as I promised, today we are looking at icing, and this is a little bit like how we see it in the Netherlands, but yeah, you can actually find it in many situations, actually in natural, standing natural processes, as well as in industrial applications. And so what we want to focus on here is the interplay between convection, flow, and phase change, and in particular here, melting or icing. Now, the setup, we make a step back, again, trying to simplify as much as possible. The system is very similar to a Rayleigh-Benard system, but with phase change. So we are considering a system where you have a top wall, but it is kept at a temperature that it is lower than 0 degrees. We consider water as a fluid, so fresh water. And then we have a bottom wall, which is typically kept at a temperature that it is larger than 0. And what we have been doing is to combine experiments, direct numerical simulation, and also simple one-dimensional models to try to get a better quantitative understanding of what is going on. Now, of course, you can imagine that in such a setting, where you have the top boundary that it is below 0, you start to form a layer of ice here. And this layer of ice may grow, of course, according to all the different parameters, how high is the system, what is the temperature of bottom. And typically in the study that we have been conducting, we have been keeping most of the parameter constant, and we have been varying only the temperature of the bottom wall, okay? So if you are in a situation where basically there is no flow, this is basically the classical Stefan problem. It's a three-dimensional cell, but eventually it is homogeneous in this direction, and it is effectively a one-dimensional system. So you'll see that as a function of time, ice will grow, and it will grow in a diffusive way up to a point where you reach some equilibrium, and you will have that the heat flux inside the ice and the heat flux in the water is exactly identical. And at that moment, you reach this asymptotic equilibrium, and the dynamics will basically stop. That's at least what happens for a situation where you have pure conduction, so no convection. Now, before moving further, just a quick view on the experimental setup. So the experimental setup, of course, is three-dimensional, but it is almost bidimensional in the sense that it is, it's not. Is larger than deeper, and it really looks like the sketch that I've just illustrated, so I don't need to spend too many words on this. On the other side, I want to say a little bit about the numerical modeling approach that we followed. So we have been doing direct numerical simulation, so we are really solving the equations that you see here on this slide. We have been using Lattice-Boltzmann method. Is not particularly important. Actually, another flow solver will work as well. So the Lattice-Boltzmann method in our case here is just a solver for the momentum and temperature equation that you see here. Now you see this is a normal Navier-Stokes equation plus some buoyancy term. I will comment about this in a moment. And then here you see the equation for the temperature inside both the fluid as well as the ice phase. And so this equation here are solved both in fluid and in the ice. And then you have an energy equation here at the interface between the fluids, but it is basically integrating an enthalpy function. So this enthalpy function here is giving you an indicator that tells you if you are in an ice region or in a liquid region. Okay, so this equation here has been proposed already quite some time back. For example, in this publication indicated here, validated and used in different contexts. We have been focusing on both 2D as well as three-dimensional simulation because of numerical convenience. 2D simulation, of course, are faster than three-dimensional one. All right, a very essential point and a novelty in our study is that we consider the density anomaly of water. Now, you know that if you take a substance, if you take a fluid, normally by increasing the temperature, the density will decrease. That's the case also for water, except in the interval of temperature between 0 and 4 degrees. Between 0 and 4 degrees, water present an anomaly, meaning that if you increase the temperature, the density is actually increasing. That's actually one of the reasons why icing starts at the surface of water. So that's something that we implement in our Bussiness term here, and in this way we model this anomaly of water. I mentioned already that we are also using a one-dimensional model. So the one-dimensional model is basically a generalization of the Stefan problem, the classical problem for icing with a Neumann solution. But now we are going to consider both the ice phase, the water layer, and something more that I will mention in a moment, which is associated with this density anomaly of water. So the equation may look like something like this, a little bit more complex. I will not report them here. All right, now the other method we have been using are already mentioned, the experiments. So this is how it looks like, a picture of the experimental setup. Maybe you can see here on the back the ice front. Normally the setup is closed, of course, to isolate it. This is a similar parameter, fully 3D simulation. And here you see the thermal plumes. Here you see, again, the surface of the ice. And this is, for the same parameter, a two-dimensional simulation. So we have been doing quite a bit of work to convince ourselves that the two-dimensional and three-dimensional simulation actually give quantitatively close results. You can already see something here. You can see that by setting different temperature of the bottom layer, you finish with a different thickness of water. H0 will be how much water you have in the system. So, you know, H minus H0 will be the thickness of ice. And what you can see here is a comparison between 2D simulation, the circles, experiments, the triangles, and the 3D simulations, which are these red dot. And there is a reason why they are only at larger temperature. Numerical simulation in the diffusive regime are really extremely slow. And so it is way less expensive to simulate the turbulence. Now, if we go to the one-dimensional model that I was just mentioning, which is basically the Stefan problem, that would be what you obtain as a prediction for the ice front position. The asymptotic ice front position at very late time, at infinity, let's say, neglecting the anomaly of water. If you include the anomaly of water, that's what you obtain. And so this is quite remarkable. It's quite remarkable because clearly this water anomaly is very important, is playing a very important role in this system, and we want to understand why and know better what happens in the system. So let's zoom a little bit more here what is going on. So we have an ice layer, and then we have a region where the temperature goes from 0 to 4, which we call stably stratified, and from 4 to eventually larger temperature, could be 6, 8 degrees, we call it unstably stratified. Now, the unstably stratified layer can either be stable or unstable according to the effective Rayleigh number in this region. And so if you consider the height of this region, which we would call H4, and you consider all the parameters of the problem, for example, this is 4 degrees, of course, by definition, and this TB, you fix it, then you can have that the effective Rayleigh number is either larger or smaller than a critical Rayleigh number. So you could have that this region here is also conductive, or could be convective, or could be even turbulent. And so indeed, we find 4 different regimes. They're kind of summarizing this slide here, but I will now walk you through one by one. So there is regime 1. Regime 1 is where the bottom temperature is smaller than 4 degrees. If it is smaller than 4 degrees, then you remain only with the stably stratified layer in the bottom. And so you see here, this is a little bit to snapshot as a time evolution. Ice position was here in the beginning, and then at the end, it is in this other position. And you have a linear profile of temperature, both inside the ice as well as in the water. So this is really the classical one-dimensional Stefan problem. Now, if you raise the bottom plate temperature between 4 and 5.1, things get a little bit more exciting. Now I will kind of try to play it again. So you see that these dynamics in the beginning is chaotic. Of course, it jumped. It's chaotic in the beginning, and you see that it's quite irregular. And later, you start to develop. Here you still have convection, but now you have a time-independent flow. And at later time, it gets, I will play it again, it gets into a conductive state. And the reason for this is that the ice front that you can see here is moving down, and because of that, well, actually also the 4 degrees line, the 4 degrees line is this one. So you see that this is the 4 degrees line, and so the unstable region gets smaller, thinner and thinner, and so eventually the critical, the effective Rayleigh number goes below the critical Rayleigh number, and so the system changes behavior and goes into a conductive state. Now this is what we call regime 3, between 5.1 and 6.9 degrees. You see that now you reach a statistically stationary state where the water keeps remaining into a turbulent flow. This solid line here is the ice interface, so is the isothermal at 0 degrees Celsius, and this other one, which is continuously moving, even in the late stage, is the 4 degrees isothermal. Okay, so you see that the 4 degrees isothermal is actually not a constant line, but it is fluctuating between H4 plus, H4 minus, as we call it here. And then there is the last regime, regime 4. Now, regime 4, you have such strong turbulence in the stable stratified region that pushes through even the stable stratified layer, and it is going to deform the morphology of ice. You see here, this is the water-ice interface, which has been bended, and so also the 0 degree iso surface changes. Now,
Federico, you have about 3 minutes left.
Okay, yes, thanks a lot. So here you see indeed the growth of ice in the different regime. And you can see that in some condition, particularly larger bottom temperature, you have a band, not just a value, but a band, because these lines are not horizontal anymore, but they fluctuate between higher level and a lower level. And indeed, this was just to show that this one-dimensional model that we developed by extending basically the Stefan argument, including the correct flux in the fluid, and considering also the stable layer, is producing quite well what we observe, even if the one-dimensional model, of course, is not able to capture the fluctuations, but just the average behavior. Last check, the time to equilibrium. So you see that for small bottom wall temperature, it takes a very long time for the system to reach its equilibrium. And if you have a stronger turbulence, it equilibrates much faster. So you can actually define a sort of time, transition time, where the diffusive behavior stops and you reach equilibrium. And you can also test that against the model that we proposed. So summary, we have combined experiment, simulation, theoretical modeling to study the coupling between change of the morphology for a phase changing problems like ice melting or icing process and the flow beneath it. And we have found 4 different regimes that strongly depend on the temperature in the bottom plate. And that even a simple one-dimensional model are actually quite good in predicting what is going on. So as a conclusion, I'd like to stress again that thermal convection, together with other processes happening in geophysical application, is extremely interesting and presents a lot of interesting physics to be uncovered. So I'd like to thank you very much for your attention.
Thanks very much, Federico. Okay, we're open for questions. Yes, Natalie.
Hi, this is Natalie. I have a burning question. If you would flip your either experiment or numerical simulation, so put the cold surface at the top and the warm surface at the bottom, would you get the flipped results as well? Does gravity play a role at all? You would think that heat rises. Is it symmetrical?
I wouldn't say it is symmetric, but so you mentioned that you put on top the cold. I'm not sure what you said, because I mean, actually,
sorry, I'll repeat it
again.
If you switch the boundary conditions, so you make the top surface
warm.
Warm. I said it wrong.
Okay.
The top surface warm and the bottom surface cold. My apologies.
Yes. Yes.
Would you get the same dynamics?
I think the dynamics, of course, would be different, but you may encounter also interesting regime in that conditions as well. So that reminds me a little bit of, for example, the problem of melt ponds, where you have ice that it is locally melting and producing a pond of water. But definitely the dynamics will be different from what we studied here.
Okay, thanks. Yeah, another question.
Hi, this is Emily DeYoung from Caltech. I was curious if you have a sense of how time variations in the top surface temperature, so for instance, if you imagine like a diurnal heating, if that would interrupt the convection that's going on somehow and have any impacts on the icing time or depth.
So we are actually not changing the top temperature here. So I'm trying to figure out, you are still thinking about the inverted setup, like the previous question?
Yeah, so I was just curious, so as a thought experiment, what's your inclination on if you were to introduce some sort of diurnal heating in the top surface, what impact that might have in convection that's going on below the surface and therefore the icing time?
So you like to have a situation with a free surface, basically, right?
I think so. Diurnal heating. In other words, for example, if you have the top or bottom boundary, I guess, changing as a function of time. Temperature changing as a function of time.
Yeah. Yeah, as I said, the problem where the temperature changes on top is slightly different, but the problem of, for example, bottom temperature here changing as a function of time may actually revert the process. So now you have seen, for example, a situation where, I mean, that depends, of course, from the initial condition you are considering. We were considering something where you start to cool from top, so ice layer needs to form, right? But if for whatever reason you are going to change now the bottom temperature, let me take the sketch once more. So if you're going to change here the bottom temperature and you are going to heat up, of course, the ice will quite rapidly start to melt and move back. So if you have some time dependency here on the bottom boundary, let's say that would be, the closest to what I presented here, you will get, of course, a dynamics also of these isothermal lines, and you can have some interesting dynamics, because as I was showing before, you may have a switch between a conductive and a turbulent regime.
This is Jeff Morris. Thank you very much. That was very educational. I was curious about whether it's possible in the experiments to put in some sort of variation of the surface features on the bottom, maybe some simple like sinusoidal shape or something, to see the interaction between the lower surface geometry and the resulting formation of ice.
So when you talk about the bottom, you're really talking about here, the bottom, right?
Yes.
So I can imagine that you have in mind disturbing the mean wind of things like that, right? You would like to put some roughness here, for example.
Roughness, or even just some simple sinusoidal smooth surface.
Yeah. Okay. So something that I didn't show here is going back a little bit to the previous slide, like third slide I showed, where there was a lateral wind. So we've been studying also a periodic system. And of course, that is going to influence the dynamics. So also in this case here, you are going to affect the plumes. Now, if you are going to put some roughness or some structure here, but it is actually interfering with the mean wind, of course, that will also produce some effect on the dynamics. Now, the remarkable things that surprised us quite a bit is the fact that even the most complex regime where you have non-flat isolines can be captured quite well in terms of a sort of mean field one-dimensional model. So I wouldn't be surprised if even that case could eventually be explained. So what we are actually doing is putting a model for what is the heat flux in the water region. So if you have, for example, a different cell that has a different Nusselt versus Rayleigh relation, and you plug it into your system, I would expect this to work similarly. I don't know if this answers your question.
Yes, it does. I'll ask you a quick question.
Please.
Yeah, this is Raymond, by the way. Just curious if you can generalize this. I mean, these temperatures are kind of interesting, 5.1 and 6.2 Celsius. So is there a way to non-dimensionalize by a generic density anomaly?
Yes, I think so. What we have been trying to do here was exactly to replicate the experimental setup. That's the reason why we have some fixed height, and that corresponds then to some fixed, value of temperature that produces non-critical Rayleigh and so on and so forth. But indeed, what counts here is the Nusselt number in the system. So similar results could be written probably in a little bit more general way. But 4 degrees is 4 degrees. So, sorry.
Kimberly Hill from the University of Minnesota. So in Minnesota, the diurnal heating that was brought up earlier it can be very critical right around the springtime. And I was curious if you have ever looked at, or someone has looked at, what happens when you change the top temperature. So it's very close to 0 C. And is there a certain point at which you see these transitions that you mentioned for a temperature either just a little bit above 0 C or just a little bit below 0 C for the top boundary?
Yeah, I think that there are some studies looking at the influence of the dynamics of the top boundary. So I will need to look into that, but I may get back to you on this.
That would be great. Thank you.
There is time for one more question. Any burning questions? Yeah, Michael.
Federico, Michael Manga. If in the ocean, when freezing happens, you release solutes. Will the release of solutes in Earth's ocean always overcome the stable stratification, the layer that sometimes exists underneath the ice?
Yeah. Yes, I do think that the problem in oceans indeed will have to be reconsidered or will be different. For there could be some situation where maybe there is a melting of fresh water, so that maybe surely it's going to be much more complex.
Okay, fascinating problem. We thank Federico, Rama, and Alfredo for joining us from far away. We wish you pleasant, whatever part of the, I guess, evening, or Rama, I don't know what time it is there. Thanks very much, Federico.
Thank you.